Welcome to everyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. You can grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, we have another introduction to calculus. If you've taken pre-calculus recently, this is right up your alley. If you have only taken Algebra 2, it would be kind of tough for you to follow along, but you can still get the general vibe of this question. The question is basically, what's happening at x equals 0? So, if you're not familiar with how to phrase that question mathematically, because it's not very mathematically written, right? What's happening at x equals 0? That's not very mathy language. So what I'm really asking for is I'm asking, what is the limit as x goes to 0 of f of x? It's basically what the instructions are implying here. I want you to find out what's the deal with what's happening at x equals 0. And to investigate that, we're really going to be looking at what's happening, in other words, what's being approached as x approaches 0, because we cannot plug in 0. If you want to give it a shot, go ahead and plug in 0. And you'll be quickly disappointed that you can't find the answer to that, because you'll be dividing by 0. So we have to do something else in order to figure out what's happening at 0. That's called the limit process. Give yourself about 4 or 5 minutes if you'd like to work this out. Maybe you saw something like this at the end of your pre-calculus class. And if you're taking calculus for a second time, that's okay. Welcome. You're still welcome. The fact that you're trying to learn and improve yourself is why you're worthy of being here. Let's get that right. So I'd like you to take 4 or 5 minutes, give this a shot, and when you're ready, you can unpause the video and join back to see how it's done here. This is a specific type of limit, which is covered in the first portion of a calculus course, also at the end of some pre-calculus courses, to kind of lead you in towards calculus. And there are a few different types of limits and algebraic manipulations that we need to know in order to evaluate the limits. Sometimes it's as easy as factoring and canceling a common factor. In this case, it's not so easy. In this case, we have a square root expression. And what's typical of these square root expressions in a limit problem is that we need to fix the fraction in some way. We need to fix it so that we can cancel the x on top and bottom. Right now, we cannot cancel these, obviously. Those will not cancel. It's not how math works. We need to create the opportunity to cancel them. And we do that with something called the conjugate. We're going to multiply the top and bottom of this fraction by the conjugate. Conjugates are like the evil twin and the good twin. See that? That's the good twin. It has a plus in between the square root and the 2. Well, since this is a fraction, everybody, we have to keep the fraction balanced on top and bottom. So I'm going to multiply by 4 plus x in the square root, plus 2 on the bottom as well. Why would I choose that? Why do I choose the evil twin? Well, we choose the conjugate to multiply because when we multiply all this out, we end up getting this nice difference of squares. In fact, hopefully you recognize this already as a difference of squares type problem, because we have the structure of a minus b times a plus b, which is going to give us this a squared minus this b squared. And in the denominator, I would recommend not trying to multiply that out. I would recommend keeping that looking kind of not so nice, looking kind of ugly, to be honest. Now, how does that help us? Obviously, the square root and the squared cancel. So on the top, we get something that's going to simplify. On the top, we're going to get 4 plus x minus 4. And this is going to allow us to cancel something really nice in the numerator. Here we have 4 plus x plus 2, and the 4's will cancel. Isn't that convenient? Because now we just have an x on top. That's going to allow us to cancel the x on bottom. Kind of bizarre how that happens and how that works out so perfectly. The problem was designed to set up like that. Let's go ahead and cancel the x's. You might wonder at this step, how are we allowed to cancel the x's if x is 0? Because we're figuring out, after all, what's happening at x equals 0. The thing about a limit, I didn't go too deep into this in this video, but the thing about a limit is that x is approaching this number, which kind of literally means that it's not equal to 0. It's something very close to 0, but it's not 0. And we can cancel anything which is not 0 with itself. So this leaves us with the limit, as x goes to 0, of 1 over square root of 4 plus x, and then plus 2. We have to write this limit every single time. It's a little bit annoying, but it's technically required, because the entire time we're considering what happens as x goes to 0, but we weren't able to plug it in because of the x on bottom. Now that we've rid of that, now we can plug in x equals 0. No need to worry about dividing by 0 now. And we can stop writing the word lim x goes to 0, because now we've actually allowed x to arrive, so to speak, at 0. So we get 1 over 2 plus 2. That's 1 over 4. Okay, and yeah, I kind of want to get a look at Desmos to confirm this. So we're going to get a little bit of Desmos Blab. Let's see. So if I ask Desmos, hey Desmos, what's happening at 0? This is what it tells me. However, you'll notice that it shows that point, or it shows that circle, at a specific y value. What y value is that? Well, this is 0.25, which happens to be 1/4. So there's the function. Here's the graph of the function. It obviously has a domain restriction due to being a even radical function. And then here at 0, we get something funky. So the 1/4 that we found here is not the actual value of the function. Rather, it's the y value where this hole is located, because the rest of the function was sort of gearing up to hit that point. But since we can't literally plug in 0, I'm sure you tried that at the beginning, right? You tried plugging in 0, and what did you get when you tried to plug in 0? You get 0 over 0. That's not anything determinable. We can't determine what that is. So this graph kind of shows us what's happening there. And to go even further with this idea, I'm actually going to encourage you to do this, but also show you the results on my table. So I'm going to get very close to x equals 0 on either side. And I'll show you on a table of values what is happening with the y values. I've plugged in some values that are negative. So -1, that would be around here. That's a y value of 0.2679. So it's already really close to a quarter. In fact, if I move this a little further, you can see that the graph sort of begins, if I plugged in -4, it would sort of begin there. Right, so it would begin at like approximately a half, but not quite a half. Anyways, let's take a look at what happens when we get closer to x equals 0. Well, from above, because this is bigger than a quarter, it seems to be getting lower and lower. This gets really close to 0.25. Then we just have this undefined blip. And then on the other side, it goes lower just below 0.25. So really, we can kind of look at things from both sides of 0. And you notice that the y value is trending towards 0.25. It's suggesting, it's giving, as you kids might say these days. It's giving 1/4. Yeah. So for clarity, be prepared to answer a question like this by using the conjugate to multiply the top and bottom of an expression, and then some magic happens and allows us to cancel out the x. We can plug our limits in, and the limit tells us where the function sort of wants to be, not necessarily where it's at. Okay, like I said, enough blab. See you guys next time.